Hey folks, welcome to this episode on gas stoichiometry. So when we're looking at stoichiometry and gases, we can start applying the knowledge that we've gained in our previous chapters. We know how to do relationship questions where we're relating one species to another. We also have to remember our limiting reagent, theoretic yield, percent yield, etc., etc. Except in this case, we're going to be solving for gases in various conditions. For example, different pressures and different temperatures and different volumes of the containers. To do this, we need to remember some of our laws. The more important ones that we'll use more often are combined gas law, which is shown over here. Now you may see it differently as well if it's the P1 V1 over T1 equals P2 V2 over T2. I just rearrange it this way because it's easier for some people to rearrange and isolate for certain variables. You'll need to know the ideal gas law. This is for static calculations where there is no change. So in this case, the pressure has changed into a new pressure, for example, and we have two different conditions. This is looking at any one of these variables in a gas as is. Now, we're using kPa as our pressure, and so our gas constant is 8.314. If you're using atmospheres, you will be using a different gas constant. And finally, Dalton's law of partial pressures. So the total pressure of a mixture is based on the pressures of its individual gases just added up together. So in here, let's do our first example. It says how many liters of chlorine gas are required to react with excess sodium metal to yield 5 grams of sodium chloride at 22 degrees Celsius and 100 kilopascals. Well, the first thing that you should see is that there is actually a relationship question because it's asking us for how many liters of chlorine gas and are used to produce this many grams of sodium chloride. So it's relating chlorine gas to sodium chloride. When we do that, we know that we're going to need to use a mole ratio. And in order to do a mole ratio, the only way of getting this is by seeing what our stoichiometric ratios are. So we're going to need a balanced equation. So once we start off with a balanced equation, we can create this mole ratio. Now, in order to get that mole ratio, I need moles. How can I get moles and put into a mole ratio? Well, I have 5 grams of sodium chloride. If I can take my mass and turn it into moles, I can then multiply by my ratio and get moles of Cl. Okay, and that ratio will be Cl2 over NaCl. And again, this mole ratio comes from our balanced equation. So how do I do this? Well, I know how many grams I have. I have 5 grams. I divide by the molar mass of sodium chloride, and I get moles of sodium chloride. Once I multiply by my ratio found from my balanced equation, I can get moles of Cl2. Now, once again, how do I use this now to get what my question is desiring, the liters of chlorine gas? Well, I have moles, which is N. I have temperature, which is T. And I have kPa, which is pressure. It's asking for liters, which is volume. Now, when I look at this, well, it's kind of easy to see because I have N. The only equation that I have that has N is my PV equals nRT. The only thing is we're missing is R, which is our gas constant, and it's given. So knowing our 4 variables, we can solve for a fifth. So this is what it looks like here. Once again, we started off with a balanced equation that includes the states, and we had 5 grams divided by the molar mass of NaCl, and then we multiplied by the mole ratio, again, from our balanced equation. We got this many moles of Cl2, and we adjusted our equation to solve for V, and with 2 significant digits, we had 1 liter of Cl2. Our second question here is the decomposition of MgClO3 or magnesium chlorate. Now, when we look at magnesium chlorate decomposition, remember that there's only one reactant, and that's the thing that's being decomposed. Now, if you remember, the decomposition of chlorates yields a metal chloride, in this case would be MgCl2 solid, plus oxygen, and we'll have it as a gas. So it's asking us for the percent yield of the gas that is created. So the gas that is created in this case is oxygen. Now obviously we need to balance this, and so all we do is put a 6 over there. Now it's asking for percent yield, so we have to go back and remember what percent yield is. Percent yield is actual yield divided by theoretical yield times 100 to get a percentage. Now it's actually saying, if you read the question, decomposes at this temperature and And this many liters of gas is created. If you remember those key words back when we were doing limiting reagents and percent yield, something that is created in the lab or created in an experiment or whatnot is our actual yield. So this 5.94 is our actual yield. So the only thing that we need to do is figure out what our theoretical yield is. Now, when we were doing limiting reagents, how did we figure that out? Well, if we had two reactants, we figured out what our limiting reagent was, and then from there we figured out what our theoretical yield is. But this is actually easier in this question because we only have one reagent. So therefore, the limiting reagent must be MgClO3 So if I only take my my grams of this, convert it into moles, and multiply by the mole ratio, again from our balanced equation, I can figure out how many moles of O2 gas are created. Once I know this, I'll look again. I have temperature, I have moles, and I have pressure. I can figure out what my volume is. The volume that I create is my theoretical yield, and I can get a percent yield percentage. So this is what we see over here. So once again, we start off with a balanced equation that we saw before. And the first thing we want to do is we want to take our grams of our limiting reagent, in this case, our only reagent, magnesium chloride, and divide by the molar mass to get moles of MgCl magnesium chloride. Now again, we want a relationship between this reactant and the gas that's created, in this case oxygen. So we multiply by the mole ratio from our balanced equation, and we get moles of O2. Again, we're looking for volume because in this case, we've created 5.94 liters, so we need to figure out what was the maximum amount that could have been created. And so we take this value of moles and put into our equation here. We use our gas constant, and our temperature is already in Kelvin. We don't have to do anything. Our pressure is in millimeters of mercury, so we have to divide by 760 and multiply by 101.3 to get 103 kilopascals. And we get 12.23 liters. So this right here is our theoretical yield. That's the maximum amount of oxygen that can be created from 4.50 grams. Now, only 5.94 liters was collected, so maybe some escaped or whatnot, but our percent yield here was only 48.6%. That's pretty low, but is the correct answer. So number 3, in this case, what we're looking at is it's saying find the pressure created by the hydrogen gas when 38.2 grams of zinc is reacted with 200 milliliters of a 0.75 molar solution of hydrochloric acid at a temperature of 88 degrees Celsius. The vessel the gas is collected and has a volume of 765 milliliters. Now, one of the things that you have to be aware of is that when we have a vessel, it's not telling you directly how much volume you have of this gas, but it actually is in this case. Because remember that a gas doesn't have a defined volume. It can be compressed or it can be expanded depending on the vessel. Again, it can be expanded or compressed depending on the volume of the vessel. So if our vessel has 675 milliliters, then the gas is going to occupy generally this amount of space. So this will be the volume of our gas. Now, one of the more important things is how do we get to this final answer? Well, we have volume, it's right here, our final volume. We have temperature, which is 88 degrees. And when we have R. Now it's asking us for our pressure. So we need one more thing to put into PV equals nRT. We're looking for P, we have V, we have R, we have T. The only thing is that we need N. So we have to solve to get N. Once we find N, we can plug it into our PV equals nRT equation and solve for P. Now the question is, how do we get there? Well, you can see from the equation that we actually have hydrogen gas produced when zinc reacts with hydrochloric acid. Now when this happens, we get ZnCl2 plus H2, and this is balanced this way. So what we're doing is we're given 38.2 grams of zinc, and we're given this value for HCl. We're given a value for each of our reactants. Once we're given a value for each of our reactants, this is now a limiting reagent question. So we find limiting reagent, and once we find that, we can figure out our moles of the gas of H2 produced, and this will be put over here to fit into our PV equals nRT equation. So this is what it looks like. Again, we start off with a balanced equation because when we're relating one thing or another, or we're doing limiting reagent, we need that mole ratio. So we started off with 38.2 grams of zinc divided by the molar mass, and we had moles of zinc. We're relating zinc with H2, and the reason we chose H2 is because that's the gas that we're looking for. It's looking for the pressure created by the hydrogen gas. So it's a 1-to-1 ratio, so we have the same amount of moles there. Now in this case, hydrochloric acid, we're given the concentration and the volume, so we need to find moles of HCl. Again, molar ratio, and we have this over here. Now the amount that creates the least the reactant that creates the least amount of hydrogen is our limiting reagent. So you can see when we compare this amount of hydrogen that could be produced and this amount of hydrogen that could be produced, this one was the lesser of the amounts. So this one is now gone, we don't use this. This value produced the least amount of H2, and therefore it is the limiting reagent right here. Now we figured out how much H2 is going to be produced, so we are looking for our pressure. So we rearrange our equation PV equals nRT. This goes over here, our constant. We have our temperature, which was 88 plus 273 to great Kelvin. And again, our volume that it would occupy is 765 milliliters. Into liters, it's 0.765. And so our final pressure is 333 kilopascals. Now this is an amazing question, and the acknowledgement for this question is in the back. I saw this and I really enjoyed it, so we're going to go through it. And this is a pretty intense question, has a lot of different parts to it. And the question is, two gases, nitrogen oxide, or NO, and oxygen, are held in two separate chambers, and they are reacted in a separate vessel to produce NO2 gas. So we start off with two gas reactants, and we finish up with the production of one gas product. Now, the initial conditions of each gas are as follows. We have NO, and these are our conditions over here. What it's asking us is, it says calculate the total pressure in the final reaction vessel. Now, right there and then, the total pressure should ring some bells and say, well, Dalton's law, P total is equal to P1 plus P2, P3 plus PP, etc., etc. Okay? So the total pressure is the pressure of the individual gases. So basically, a basic way of thinking about this is we need to figure out the final pressures of all these individual gases. Now, which individual gases? Well, our reactants and our products. Okay? So in order to do this, we first have to figure out how much NO2 is going to be produced. Now, how do we figure that out? Well, we have two reactants, and we have conditions for both reactants. So the first thing that we need to do is figure out our limiting reagent, because we want to find what the theoretical yield of NO2 will be. Okay, so let's do that first, and then move on from there. So this is what it's going to look like. Again, when we're looking at limiting reagents, we have to do a balanced equation. And when we look at these conditions, initially we might not think that we can actually get moles from this. But remember, with the addition of our gas constant, we can figure out N by just rearranging the formula. So again, we converted the torr into kPa, and the kelvins we left, the liters we left. And so we plugged this in, and we got this many moles of NO, this many moles of O2. And then, so we figure out our moles. We now want to figure out our limiting reagent. So we look at the relationship between this reactant and the product that we're forming. Again, same doing over here through our balanced equation. And we figured out that this much was produced of NO2. Now again, the reactant that produces the least amount of product is our limiting reagent. And you can see from the two that this is the higher amount. And so our limiting reagent is our NO, with 0.077463 moles of NO. So this is our limiting reagent, and this is our theoretical yield in terms of moles, not in grams. This is our theoretical yield of NO2. We're going to need to use this value a little bit later on. So our next step is, so our limiting reagent, we figured out. And if we remember our P total, I'm just going to say our P total is equal to PNO plus PO2. These are our two reactants, plus PNO2, our final product. Now, our limiting reagent, if you remember, gets used up completely. I'll say that again. Our limiting reagent gets used up completely. So if there's no moles anywhere of our limiting reagent, that means no pressure can be created from no moles. Okay? You need to have particles of something to bounce off walls to create pressure. If it's used up, there's none remaining. So our limiting reagent is NO. We can actually get rid of this term. So our P total is actually equal to PO2 plus PNO2. Now, why O2? Well, remember, it's the reagent in excess. It didn't actually get completely used up. So what we need to do is our final total, which is what we're being asked for in the question, the total pressure on the final reaction vessel, our P total is going to be equal to the pressure created by the oxygen molecules and the pressure created by the NO2 molecules. Now, if oxygen is not the limiting reagent, that means it's the excess reagent. So what we have to do is we have to figure out how much oxygen or how many moles of oxygen are remaining or left over after the reaction has happened. So once again, here our P total is equal to this, but we know that our limiting reagent is completely used up, so that's no longer part of our equation. I'm going to leave it in for now, and I'm just going to call it 0 moles, which doesn't affect it. So what we need to do is we have to figure out how much O2 is left over. So remember, to figure that out, left over is equal to how much we have minus what we used. Now, we already figured out how much we had through our previous example, or not our previous example, but the previous page, just by converting our reaction conditions into moles of O2. To figure out how much we used, we need to use the value of our limiting reagent and use a relationship between the two reactants. And this is how much oxygen was used. So again, to get left over, I take out how much I had minus how much I used, and this is what I have left over of our oxygen. Remember that the limiting reagent is the thing that controls the reaction and controls how much of the products are made and how much of the other reactants are used. So that's why we are using this value over here. So at the end of this reaction, we're assuming that it goes all the way to the right and doesn't kind of go back and forth. At the end of this reaction, we're going to have 0 moles of our limiting reagent because, again, it's used up. We have this many moles of oxygen left over, and we already figured this out. This was our limiting reagent of NO2. Now remember, the question's asking us for P total. So it's the pressure of our NO, which is 0. We can pretty much get rid of it. Our PO2, we have this many moles, and our PNO2. So we have to convert these moles somehow into the partial pressures. So to do that, what we need to do is figure out what the P is using PV equals nRT. Now, you have to kind of ask, well, couldn't we use just the initial pressures? No, because remember, if you go back, there was a final reaction vessel where the two gases mixed. We had 4 liters of one gas and 2 liters of another gas in one kind of, let's say, flask and the other in another flask. Now, what happened is that they were both mixed into another flask. Okay? Well, if I put 4 liters of gas of one gas and 2 liters of another gas, what's my total? 6 liters. So this is what's happened. We've actually changed the conditions for our gases. Our gas that started off with 4 liters, so this was our initial, now has 6 liters. Here, initial, final over here. So we actually changed the volume that the gases could occupy. And because we did that for each gas, we now have a new pressure. So using our new volume, and that's just shown over here, our V final, we use how many moles of O2 we have left over. O2 over here. How many moles of NO2 is produced, our gas constant and same temperature, in our new volume. And our oxygen, how many was left over, gas constant, temperature, and our new volume. And what we see here is this is our new pressure of each gas. So to figure out our final pressure, again, this is our limiting reagent. 0 moles are left over, so that means zero pressure is produced, plus our pressure of oxygen, plus our pressure of our pressure of NO2 and our pressure of oxygen, and we get a final count here. We have 49.63 kPa final pressure. Thanks very much for watching, guys. See you soon.